We have now two approaches to deal with the Hopf bifurcation. We can either use a central manifold reduction, or we can use multiple scales. And both approaches worked fine, except that we're kind of confused that they lead to equations that are actually very different. It's not clear why these equations are equivalent and why they should be equivalent in any way. It turns out they are, but this is really kind of puzzling. And so it's worth looking at that more carefully. Also, doing that, we'll find out what the universal form for the equation for a Hopf bifurcation is. And we get sort of a tool that gives us in general an idea what the universal equation for a certain bifurcation is. When I say universal equation, I mean the normal form. We used the word normal form before. I just wanted to use sort of expression of expressing the universality more explicitly. Anyway, so let's look what we have. We have for our multiple scales approach, what we got for our simple model was the equation was dA by dt, where t was a slow time, equals 1/2 mu2 times 1 minus I times A minus 8, 1 plus I, A absolute value squared A. Okay. So what's important to emphasize? Well, the important thing is that we only have one nonlinearity, and that's a cubic nonlinearity. And it turns out that nonlinearity has a special form, which you can appreciate by noticing that there's always a simple solution of the form some magnitude times e to the I omega t. You can simply calculate that solution. The point is, because this nonlinearity here has only the absolute value squared, this overall phase cancels out from all three terms. And so therefore you actually get a solution like that, where A is given by 1/4 square root of mu, and omega is equal to minus 5/2 mu2. The numbers don't matter, but the point is that there's a simple solution like this, which in the complex A plane, if this was the real part and this was the imaginary part, just corresponds to a circular orbit. It's just a perfectly circular orbit. If you contrast that with what we found from the center manifold, there we found an equation that looks very different. It was dA, and let me put a tilde on it because it's a different A, dA by dt minus IA tilde plus, and then we had some linear term. I'm not going to write that out. Well, it's not clear how I should do that. I'll write it out. There's A tilde, and actually then there's even an A tilde star, and then come a number of quadratic terms, and I'll just label them as A20, A tilde squared, plus an A11, A absolute value squared, and then an A02, A tilde star squared. And so, as we said before, this has only quadratic nonlinearities, and a whole bunch of them. And even the linear term has like a complex conjugate. And it clearly does not have a simple solution like this. So that's kind of confusing at first sight. Of course, we have to remember A and A tilde are not the solutions in the original system. And so it turns out they actually measure different things in the original system. In the center manifold approach, we had that x and y were given by some linear transformation times the A, the imaginary and real part. So essentially it was just a transformation in the plane, in the phase plane, a linear transformation. So the xy coordinates and the AR, AI coordinates are pretty much the same. Not much has happened. Whereas in the multiple scale approach, the connection is more complicated, or more evolved, maybe I should say. So there we have that x and y are given by, well, there's an epsilon, then there's this amplitude times an eigenvector times e to the it, and then the complex conjugate. And then at order epsilon squared, we have further terms. I'm not going to write them out. We have e to the e2 0, then we have u2 2 e to the 2it plus u2 2 star e to the minus 2it. And then in principle, we have also order epsilon cubed and so on, which I'm not going to write out. So clearly, if x and y are the same, the a's, the two a's, the one without and the one with, oh, I forgot the tilde here. These are tilde guys. The guys with tilde and the guys without tilde are very different objects. In particular, you note that even if we have this very simple solution in the multiple scale analysis, where we just have e to the I omega t, where we only have one Fourier mode here, the real solution, x and y, they have higher order Fourier modes as well. They have the harmonics with frequency 2, frequency 3, and so on. So there are all these higher harmonics, which in the center manifold approach here, a tilde must be in the A already, we assume. I mean, that would make sense. If x and y are the same, then they would have to be in there. And so the question arises whether one can find a transformation between the A tilde and the A, such that this equation, the center manifold equation, has the same form as the multiple scale equation. And because to leading order, they're the same, it's just that this multiple scales approach has then higher order in epsilon, higher order terms with higher frequencies. So that transformation going between the two should be something that's called a near identity transformation, which is sort of just making small changes, which only are the changes are only in higher order in A. So that's what we're going to try. We're going to introduce what's called a near identity transformation. And well, so let's write it down and see how to deal with that. So we would have now, let's say A tilde is simply given, no, let's write it for A. So A is given by A tilde plus higher order terms. So let's say we could allow alpha times an A. No, I'm sorry. I mean, one can do it either way. I just want to do it the same way as in the notes. So let me start over. I'm sorry. So let's say A tilde is given by A plus an alpha times an A squared, plus a beta times an A absolute value squared, plus a gamma times an A star squared. Plus, I want to do cubic terms also for a reason that become apparent later. So we have delta A cubed, then we have a sigma A absolute value squared A, and then we have a rho A star squared, and then higher order terms yet. Okay, so this is a mapping from A to A tilde, but we really want to have a mapping that goes back and forth, right? And so how do we go back from A tilde to A? Clearly, this thing is not invertible in general because this is a high order polynomial. If you want to solve for A, first, it's pretty much impossible, and second, it's not unique. However, if you assume A is small and you're looking at the solution where A and A tilde are close to each other, then the transformation becomes unique. And so the inversion one does in an iterative manner, order by order in A. So let's do that. So see explicitly how that works. So we'd say A, we want to solve for A. So clearly A is equal to A tilde minus alpha. Well, my alpha A squared, right? So maybe I should write that first. Then we have a beta A squared minus gamma A star squared. And let me ignore the next terms. Okay. So what do we do with that? That's not really an expression for A yet because we have A on the right-hand side. But because A is small, what we can do is we can replace A here again by this A, as in this A squared, we insert A tilde minus corrections. So let's write that down and see that if we do that, we generate corrections at higher order. So this would be a tilde minus alpha times a tilde minus alpha a squared minus beta absolute value squared a minus gamma a star squared, and so on for the other terms. I don't have to write that out. And now you see that we get an alpha a squared. And then the next, sorry. And I did one thing wrong, right? I was carried away with writing too many things. Let's make sure I do it right. We need to do minus alpha a squared. I forgot the square here. That's the most important part. And so we see that this is a tilde minus alpha a tilde squared. And then the next terms would be all these other mixed products, which there is, for instance, the term plus alpha squared a tilde a squared, and so on. And these are all order a cubed, right? And so in fact, we see that we can do this order by order, this step order by order in all these terms. We could in principle now again say, well, this a here, this a squared, is going to be replaced by a tilde minus this stuff, which would give us a tilde squared plus other corrections. And so we can determine that inverse order by order in a tilde. So inverse iteratively. And that works because we assume a is small, and then the transformation, all these things are just small corrections. Okay, good. So what's the point now, or what's the plan? The plan is that we have here this relatively complicated equation, and we'd like to write this now, not in terms of a tilde, but in terms of this a, and we can pick these coefficients alpha, beta, gamma, and so on as we please. And we'd like to pick them in order to get rid of all as many terms as possible. You know, even if we didn't have this multiple scale result, we could say, well, can I pick alpha, beta, gamma so that I remove a whole bunch of these nonlinear terms to make the whole problem simpler? In our case, we also have in the back of our mind the idea that when we do that, hopefully we'll get the equation back that we also calculated from the multiple scales. But in principle, then the identity transformation is really meant to remove as many nonlinear terms as possible. So let's try that. This turns into somewhat of an algebra thing. I will not go through it in all detail, but let's get started though. There's one thing that we need to point out. Let's go back. So we are interested in this thing in the vicinity of the bifurcation point, right? The whole equations, all these equations are only valid near the bifurcation point. And in particular, we're interested at the bifurcation point. So that means whatever transformation we make, we want it to be valid even when mu is equal to 0. Well, that may sound sort of like a inconsequential kind of request or requirement, but it turns out that when mu is equal to 0, certain transformations are not possible. We'll see that explicitly. And so therefore, and that determines then the normal form actually. So therefore, since we really want to make sure that at mu equals 0 it works, let's just set mu equals 0 right away here. Okay, so we set mu equals 0. So at the bifurcation, mu equals 0, or mu2 equals 0, right? We called it mu2. No mu, because we're talking about the center manifold approach, so it's actually mu. Okay, mu is 0. Fine. Okay, so what do we need to do? We need to take our center manifold equation and now insert a tilde, the expansion of a tilde, everywhere in the time derivative and in all the terms on the right-hand side. So that gives a whole bunch. So let's sketch what the main things are and see what's going to happen. So we start with the time derivative. So we have d by dt, and this is normal time. And this is in principle a tilde, but a tilde is given here by a plus alpha a squared plus beta absolute value squared plus gamma a star squared plus stuff. Let me leave it at that. And then we have the right-hand side. Let me not write down the right-hand side yet, but let me rather write out the time derivative now. So what is that? That's a dA by dt plus 2 alpha a dA by dt plus beta a dA star by dt plus beta a star dA by dt plus 2 gamma a star dA star by dt. Okay, so that's this, plus higher order terms. Then what do we have on the right-hand side? Well, on the right-hand side, we have minus IA, and then let me only write down one term, 80t a squared. Okay, let's write those guys down. So we have a minus, let me do that here, minus IA, a tilde, which is a plus alpha a squared, plus beta a absolute value squared, plus, and so on, plus a 2, 0, a, well, I want to stick with the right notation, a tilde squared, which is a plus alpha a squared plus beta a absolute value squared plus, and so on, squared plus stuff. Okay, now the fun can begin. So again, this is to be thought of as an expansion in A. And so we look at this at each order in A. So we just compare these guys with these guys at each order in A. So at linear order in A, we have a dA by dt. So let's look at order A. On the left-hand side, we have dA by dt. And on the right-hand side, we have this guy. And that's it, because this guy is already inside the square. So we have minus IA. Okay, fine, that looks simple enough. Let's go to next order. Order A squared. So now we have, for instance, here a term A dA by dt. What do we do with this dA by dt? There's no, on the right-hand side, there's no dA by dt. We can't balance them. And we already have a differential equation for dA by dt, so we can't have another one for that. However, dA by dt is given to leading order by this. So we can replace now, when we go for the quadratic terms, we can replace dA by dt by this minus IA. And so that means we get now, at the next order, we get 2 alpha a times minus IA plus beta a, and then comes dA star by dt, which is plus IA star. And more terms. I'm not going to write it out. It's getting overwhelming, so to speak. Minus I alpha a squared on the right-hand side. And then there's a minus I beta a absolute value squared. And then let's just make sure we get one term from here. We get a plus a 2, 0, a squared, and more terms. Okay, so now what is the point? The point is we want to have as few terms, nonlinear terms in this equation as possible, right? So that means we have now, for instance, if you look at a squared terms, here's an a squared term, here's an a squared term, here's an a squared term. And actually, there's no other a squared term. So if we now pick a2, 0, just equal to this coefficient plus this coefficient, all these terms will cancel, and there will be no a squared term in that equation anymore. And that you can do. I'm not going to write it out. I'll just state that you can do it, and I'll give you the answers just to, you can check it yourself. In the notes, I added a few more steps in between, but there's nothing interesting going on at this point. At the next order, there will be, but here there's nothing going on. So we can choose as I said, we can choose. Oh, I said it wrong. The idea was correct, but I said it wrong. What are the knowns? What are the unknowns? The knowns is the A20, right? We are actually, this is given. This is our original equation that we derive with the central manifold approach. The unknowns are these coefficients alpha, beta, gamma. So we want to pick alpha such that the A20 term disappears. Okay, we can do that. It's the same thing. It's just reading it, the same equation the other way around. So alpha is actually given by IA20. And similarly, you can calculate beta, and it turns out to be minus IA11, and gamma is equal to I third minus A20. The important upshot is we can remove all three quadratic terms. So that's of course good, because now the equation is way simpler. Actually, to leading order, to quadratic order, the equation now looks just like this, to quadratic order. Well, that's not good enough because we know we need a nonlinear term. So we go to one more order, but we got rid of all the quadratic terms. So now, of course, the real question is, can we do that at all orders? Can we now proceed and at each order we remove all the nonlinear terms? In which case, the final answer would be simply a linear equation. That would be nifty. That would be nice, interesting. Turns out the answer is no. And that is somewhat more subtle, or yeah, subtle is maybe the right word. And it really hinges upon our requirement that we want to have that description be valid at the bifurcation point when mu is equal to 0. Turns out, and I'll state that and you can confirm it with your own calculation, when mu is not 0, you can remove all cubic terms also. You can remove all terms when mu is not 0. But that's not interesting because the activity, the action is at near the bifurcation when mu is equal to 0. So if you now go to a cubic order, and so as I said, I'm not going to do the calculation. It's better than with Mathematica or Maple. And for illustrative purposes, I'm now allowing mu to be not 0. So we see that when mu is not 0, we could do it, and we see what would happen when then mu goes to 0. And so when you do that, you expand, and then compare terms. You find that these coefficients, there was a delta. It turns out that's some number order 1. And then, of course, with correction in mu, but when mu goes to 0, that's just a fine number. Similarly, the number rho is some order 1 number. It's a complicated expression in terms of all these cubic coefficients, but it's a number. And the same thing is true for tau. It's some order 1 number. However, sigma turns out to be 1 I3 times 2a02 absolute value squared plus 3a11 times a11 star minus a20 divided by mu. So that's the important part. This is divided by mu, so sigma diverges when you go to the bifurcation point. Now that's not acceptable because sigma, what is sigma? Sigma was the coefficient of the absolute value squared a term times a. And that coefficient would go to infinity at the bifurcation point. And therefore, this transformation would become invalid because it's an expansion in A, and if your coefficient diverges, that expansion is not well ordered anymore. So that's the main result. It's not obvious from what I told you, and it's also not obvious from when you do the calculation the way I just sketched it, as in you just plug in and try to remove terms. When you do that, you just find out that the term involving sigma just drops out of the equation. You don't get to choose sigma. So it's not clear why that is the case, and we'll get to that somewhat later to get a better understanding why that is the case. But we find out that for mu equals 0, we cannot remove, and which term is it? It's a term associated, it's a term a absolute value squared times a. We cannot remove that term. So that means once you've done all these transformations, you actually still get an equation. And let me just write down what you get in this case. The final answer to cubic order is then given by dA by dt is equal to minus IA minus 2 times 1 plus I, A absolute value squared A plus order A to the 4th. Okay, so what do we do with that? Well, let's look at it and compare with what we have in the multiple scale analysis. First, okay, remember this equation here is now at the bifurcation point for mu equals 0. So for mu equals 0, we have in this multiple scale analysis, we have no linear term. Here we do have a linear term. So is that bothersome? Well, it's not, because this is actually in terms of the fast time. We didn't introduce a slow time. And so in the fast time, indeed, x and y have an e to the it, right? Sitting right here in the multiple scale approach. We factor that out up front. In the center manifold approach, we don't factor out any fast times. There's no fast time, it's just the time. And so A indeed has to oscillate with that frequency 1. And then we have a nonlinear term. Now that nonlinear term depends also on the normalization that you've picked. Essentially, how big is V? What is your eigenvector V? If you change this eigenvector here, the amplitude A will have to change even if X is the same, right? And so it turns out, the way we did it, that this coefficient is not the same as in the multiple scale analysis. However, they can only differ by a scaling factor. And so therefore the ratio of the imaginary to the real part, that cannot change. That must be the same in both cases. And that is hopefully the case. It is the case, right? No, that was not my fault, sorry. It is the case. Just here we have a factor 8 and there we have a factor of, what is it, 2. So it was just a different normalization of the vector. Okay, so we have now seen that the two approaches are equivalent. And to make it explicit when you do a normal form transformation using a near identity transformation. And we notice that when we do that, we can remove a whole bunch of nonlinear terms, and we do that at each order in the calculation, right? So at order quadratic, we removed all the terms. At the cubic order, we also removed a bunch of terms, right? But we couldn't remove all of them. We were left with this term. And so we could do this now at all orders if we felt like it. And so at each order, we could remove some terms and some we could not. And the effect of the terms that we do remove would be pushed to higher orders in expansion overall. So there's a subtlety which I just want to mention, so you've heard about it before, but we won't talk about it much at all. So you can remove a whole bunch of terms in this power series, and you push them to higher order. So you could imagine, well, maybe you could get rid of at all orders. Yes, well, yes, but certain terms you can never remove because it's not clear that in general this power series is really just a power series. If your original equation, I mean, if the expansion you did had terms like e to the minus 1 over a in it, this has, as in power series, the power series of this thing is identically 0. And so if you were to expand this, you wouldn't get anything. And so terms like this, you would not capture with any kind of approach like that. And so these terms beyond all orders, you cannot remove. And they can play an important role in certain situations like heteroclinic orbits and stuff. But these are more subtle things. But let me mention another subtle thing, which also we will not be able to talk about much. The fact that we don't separate the timescales here and we separate in the other case doesn't make a difference in certain cases. Because you could imagine situations, and again, heteroclinic orbits are among those cases, where there's a coupling between the fast and the slow time. And when they're coupled, that coupling is not captured in the multiscale approach. And so there we would get we made an approximation which is, has its impact. But these are subtle things. So for most situations, the multiple scale approach is fine and essentially equivalent with a few caveats to the center manifold approach.